princípios de ligas o bismuth para a clivagem fotocatalítica da água.
So hello everyone, and thank you for being here. I'll keep on the mask, and the reason is because I've been under the weather for most of this week, and this is why I didn't come for the rest of the conference. I thought it could have been my fourth COVID, but actually it was only a throat infection. In any case, I'll keep the mask, and I hope you can hear me in any way. So I thank Leandro very much for introducing the topic of green hydrogen production, and I'll carry on from where he stopped, or better putting, I'm going to just look at other aspects of the questions that Leandro have raised. And so the photoelectrochemical cells, as Leandro has mentioned, are devices that use sunlight, store sun energy in the form of chemical bonds, in this case, hydrogen. This is obviously very interesting because when you have a photoelectrical device, the energy that is produced has to be used immediately. And in the case of photoelectrochemical cells, you can store this energy to use whenever it is needed. So the working of this device, in this case here, there is a semiconductor material, which is called a photoanode. Where is the pointer here? Is there a laser pointer?
Yeah, this one.
Okay. Okay, so this is the photoanode, and in this case, the anode, because the holes will migrate to the surface of the material, whereas the electrons will travel through the circuit to the counter electrode, which is usually platinum, and complete the conversion of water into oxygen and hydrogen gas. So what does a material need to be a good candidate for such an application? You need good optical absorption of visible light, because 95% of the radiation produced by the sun is within the optical spectra. So a band gap between 1.6 and 2.4 eV. You need to have a favorable alignment of the band edges of the material with the redox potential of water. You need the material, obviously, to be stable in water, resisting to photocorrosion. And you need the electrons and holes to have long drift lengths and long lifetimes in the material. Now, this material here, bismuth vanadate, has been proposed in the end of the 1990s by this Professor Kudo. And it is non-toxic, it is stable, it is resistant to photocorrosion, sorry. The band gap is appropriate. And if you look at this graph here, where you can see the alignment of the band edges of several materials with water's redox potential, here you will find bismuth vanadate, right? And if you pay attention, what this graph here is showing us is that the conduction band of bismuth vanadate is slightly above the redox potential of hydrogen, which means that you need a very slight bias to drive electrons from bismuth vanadate to hydrogen, right? So in any other case, you would need basically to spend the energy that you are producing in order to drive electrons from the photoanode into hydrogen, not in this case of bismuth vanadate. So with all these theoretical aspects of bismuth vanadate, it is the material that has one of the best theoretical limits for the production of green hydrogen. In reality, however, it doesn't work too well. And it doesn't work too well because the mobility of carriers is very low. The drift length of carriers is also very small. and there is a very high rate of recombination of electrons and holes. So although theoretically the material should work very well, in practice it does not, right? So this is why several strategies have been attempted to improve the performance of bismuth vanadate, right? One of these is constructing heterostructures of bismuth vanadate with tungsten oxide, for example. Doping the material, tungsten and molybdenum have shown the best results so far. Formation of alloys, and also epitaxial deformation, right? So these are some attempts. And although epitaxial deformation has not been experimentally attempted with bismuth vanadate yet, it has been attempted with other photoelectrochemical materials, and it did show promising results. So I'm going to discuss with you today these two first aspects here, which I forgot to mention at the beginning, is work that I performed with Anasio, who is now a postdoc with Alexandre, and he's not here today because he's preparing for a concurso. So we used DFT simulations based on VASP code, so plane wave basis set within the GGA PBE approximation. And of course, at the energy cutoff of 500 electron volts, we used different supercells for our simulations. And this is some comparison between our parametric data and parametric data from other publications in the literature, both experimental and theoretical. So this is what bismuth vanadate looks like. This structure here with these distorted octahedrons is called the scalite. So the electronic structure of bismuth vanadate, the conduction states, the valence band top is composed of bismuth S states and oxygen P states, whereas the conduction band is dominated by vanadium D orbitals. The band gap is slightly indirect, about 2.4 electron volts, but if you look at the direct gap, it's not much larger than that. And in the first part of our studies, we decided to look at the effects of doping bismuth vanadate with molybdenum. And it goes mostly on vanadium sites. This has been tested in several other publications, not only by us. But what we did here is we tested complexes of molybdenum in bismuth vanadate at 3 different distances from each other. So 4 angstroms, 7 angstroms, and 10 angstroms. So molybdenum in bismuth vanadate behaves pretty much like vanadium. Its contribution to the electronic states happen most at the conduction band. Since molybdenum has extra electrons relative to vanadium, the Fermi level is shifted upwards. And the concentration of these defects in the material can be estimated by Boltzmann's factor. And it is related to the formation enthalpy of these defects. And in this case, it can be calculated through first principles. We have not considered here the entropic term for this formation enthalpy. And we can compose this kind of diagram here, which takes into consideration the stability limits of bismuth vanadate with the competing phases that can happen. And then you can have an idea of the chemical potential of the atoms involved in the formation of the material. What is the acceptable range between each? They can vary. So we call this condition here B, which is towards rich in bismuth, poor in vanadium, and condition A, which is rich in vanadium and poor in bismuth. So as you can see, molybdenum on vanadium sites, the positive slope here means that the defect complexes has given electrons to the system, so it is a donor, and this is a very shallow donor. So this is already a plus for the purpose of photoelectrochemical cells, because the more electrons that you have available to oxidize the hydrogen ions, the more efficient the photoelectrochemical cell will be, right? So the formation energy is fairly low, and these are fairly shallow defects. So these are good aspects. Now, when we look at the formation energy of the defect complexes at different distances, we have a surprising finding, which is the defects tend to be closer to each other, even though they are both positively charged. So if they are positively charged, we would expect them to repel each other. More than that, when the defects are closer to each other, they introduce a larger lattice strain in the material, which is also contrary to the idea of keeping them together, very close together. So this result here is very counterintuitive, even though the differences don't seem so remarkable, they are meaningful in any case. So we decided to investigate what is going on here. Why do molybdenum defects tend to clusterize in this material, which is counterintuitive? And looking at the literature, we found this paper here, and I'm sorry, this is wrong here, right? Because these authors, they tested molybdenum on vanadium sites and tungsten on vanadium sites, and both are donors, so both are positively charged, and they also attract each other. But these authors here did not offer any explanation on why that was happening. So this is what we wanted to investigate in the first part of this work. So the first question that we wanted to ask is, how about the strain energy? Are the defects, when they are closer to each other, indeed straining the material more than they are when they are farther apart? And we evaluated this strain by this little formula here, just looking at the position of the atoms in the system relative to the pristine system. And we came to the conclusion that indeed, when the defects are closer to each other, the strain that is induced is larger than when they are farther apart. So no surprises here. We reproduced what we expected. When we looked at the difference of charge density on the defects in the three different configurations, in all honesty, we couldn't tell much from these images here, right? So what we see is that the red areas are areas of electron depletion, but we don't see really nodal structures that could hint to what is happening here, right? So we can see that the overlap is larger when they are closer. This is not surprising, but this does not explain why these defects prefer to be in this configuration. So we tried the crystal orbital Hamiltonian population, which is a way of telling the contribution of bonding and anti-bonding or even non-bonding states into the crystal system. So when we look at that, again, it's not easy to see, but here, when you have anything positive, it means bonding states, and when you have anything negative, it means non-bonding states or anti-bonding states. And so we looked at the different bonds in the material, right? Bismuth and vanadium don't really bond If you remember the crystal structure, they are pretty further apart. Vanadium and oxygen bond, and we have these green images here. Molybdenum with molybdenum is in black, and molybdenum with bismuth is blue. So you can see that molybdenum with bismuth is mostly anti-bonding. So these images here don't tell us much yet. So we had to integrate these results and get a better look at them. So what we see now is that molybdenum with oxygen, indeed we have a larger contribution of bonding orbitals when the defects are closer to each other, and this bonding contribution slightly decreases when they are further apart. And molybdenum with molybdenum also has a bonding contribution when the defects are closer to each other, and it vanishes when they are further apart. So our conclusion here is that the reason why, despite the larger crystal strain that is introduced by the proximity of the defects, and despite the electrostatic repulsion that the positive defects cause on each other, the gain in energy due to the hybridization of the electronic states of the molybdenum turns the system more favorable when the defects are closer to each other, right? So this has been published already, and so that was the first part of the talk that I wanted to tell you. In the second part of the talk, I'm going to discuss with you alloys with bismuth vanadate and molybdenum. So experimental results have shown that alloys of bismuth vanadate with molybdenum have shown an increase in the photocurrent from 2 to 9 times. But more interesting, there is an optimal point of the concentration of molybdenum at which this happens. And this graph here, for me, was very intriguing when I first saw it, because it shows that the photocurrent increases until an optimal concentration for molybdenum, and then it drops again. And likewise for tungsten, it increases for an optimal concentration, and then it drops again, right? So it is similar to what I discussed with you in the other part of the presentation. There must be competing forces here pulling in different directions that cause the system to find an optimal point in between. And what we wanted to find out is why this is happening. So chrome is always bad because it introduces deep levels in bismuth vanadate. So it is not basically a shallow donor. Okay, so for these simulations, we used supercells with 216 atoms so that we could test different concentrations of molybdenum. And so we tested all these different concentrations of molybdenum, and we also used smaller supercells in which we could test larger concentrations of molybdenum in the material, reaching unreasonable limits of 100%, in which the material is clearly not stable, not viable, okay? So this is only a theoretical construct to help us to find trends. So when you have a supercell, you can use a code to unfold the band structure of the supercell into the band structure of the primitive cell. So here we have used an unfold code to produce the band structure of bismuth vanadate with different concentrations of molybdenum, 25%, 50%, 75%, and 100%, right? So by doing this, we have access to the band structure. We have easy access to the band gap, which we could have without having to resort to this technique. But more interesting, we have access to the effective masses. And So the band gap monotonically increases when you increase the content of molybdenum in the material. Now, this is not good for the optical absorption, right? So when you increase the amount of molybdenum, the band gap is constantly increasing. The optical absorption should be decreasing somewhat when this happens. Now, if you look at the alignment of the conduction band of bismuth vanadate with hydrogen reduction potential, so you take the pristine material, which we know from experiment that is 0.2 eV above the reduction potential of hydrogen. So we took this level here as being 0, and we observed how the alignment of the band edge varied when we varied the concentration of molybdenum in the system, and we see that the alignment worsens. So the conduction band of the material is raising above the hydrogen reduction potential, which means that we need more energy to transfer electrons from the alloy to the hydrogen. So this again goes against the performance, the best performance of the photoelectrochemical cell. So far, the two aspects that I have shown you all go against the idea that increasing the concentration of molybdenum in the system should be positive. So we looked at the effective mass of the material, and we did the geometric mean of the effective masses in 3 linearly independent directions at the band edges. And what we observe here is that the effective masses of electrons reduces monotonically as you increase the concentration of molybdenum in the system. And the effective masses of holes, on the other hand, monotonically increases. So this is something that has to be looked at with a grain of salt, because for these materials, since it is a photoanode, the quasi-particle that has to travel the largest distance are the holes, okay? Because the holes will go to the surface of the material and reduce oxygen ions, whereas electrons go to the counterelectrode. So again, the increase of the effective mass of holes doesn't seem to be a promising effect, but we have to look at that with more care. And another aspect that we have to look at is the exciton binding energy, what happens with it when we increase the concentration of molybdenum. So the exciton binding energy can be estimated by the one-year model. So it depends on the reduced mass of the electrons and holes in the material. And we have calculated it here. And what we see is that, again, it monotonically increases as you increase the concentration of molybdenum. So even though the increase is not dramatic, pretty much everything that I've shown you so far doesn't hint to the material performing better when the concentration of molybdenum is increased. However, there is an experimental data that shows that this is the case. So the next aspect that we wanted to look at is the electron-phonon coupling. And this can be estimated through the deformation potentials. This technique has been introduced by Chris van der Waal and Richard Martin back in 1989. And it's a pretty standard technique. I'm not going to stand here. But the mobility of the carriers can be estimated by this formula here. And it is proportionally inverse to the effective masses and to the deformation potential. So here are the results. Okay, so here I add the exciton binding energies that we have already evaluated, the effective masses, plus the deformation potentials. And now here, we see something interesting, because the deformation potentials, they do show a minimum at the concentration of 0.25, okay? And if we plug this into the equation for the mobility of electrons and holes, we see that there is a significant increase in the mobility of holes and electrons at this concentration of 0.25. So putting all this together, we know that when the material is doped with molybdenum, it's going to have a larger concentration of electrons. And we know that this is favorable for the working of a photoelectrochemical cell. At lower concentrations of molybdenum, there is an increase of mobility of electrons and holes, although only the effective mass of electrons is diminishing, is reducing. So this is due to the fact that the deformation potential has a minimum at 0.25% concentration of molybdenum. When you increase the concentration of molybdenum, pretty much everything else works against the performance of the photoelectrochemical cell. The optical absorption is reduced, the exciton binding energy increases, and the electron phonon coupling will increase, and also the scattering of carriers will tend to increase when you increase the entropy of mixture of the system. So this is it. Thank you for your attention, and I'm open for questions.
Questions?
Thank you, Cedric. It seemed to me that the exciton binding energies are quite large. Do you understand why?
Honestly not, Pedro. I haven't looked at other materials. This is the first material that we evaluated the exciton binding energy. So I don't have much of a feel to tell you if it's very high. I haven't seen anyone else calculating the exciton binding energy for this system.
Hey, Cedric, thank you very much. I know this work, I really like it. Just some details that I don't remember exactly. Why did you choose molybdenum?
Because we had experimental data on molybdenum, right? And from the experimental data that we had, it was the material that performed best, right? So this is the green curve here.
Okay. So if you use, for instance, niobium, like an element in a column before or after molybdenum, what do you expect to see in this behavior here?
So, Lydia, molybdenum has 2 extra electrons relative to vanadium. Mm-hmm. So it is a shallow donor. It will increase the concentration of free electrons in the material, right? So niobium will add 1 less electron to the system. However, the other aspects that I have discussed here, I would really have to run the calculations to see if it's viable. But also, niobium is not as available as molybdenum, if I'm not mistaken. It's maybe not as common, let's say, or cheap. But yeah, could be attempted.
Further questions? Okay, so if not, there are no further questions. Let's thank the speaker and all the speakers of the session. So we return in 20 minutes at 11:30.